I think that's good. Yep, I think it's recording. And I'll say good evening to everyone. This is Paul, NO0T, for the Front Range 6 Meter Group and the Deep Space Exploration Society, who's joining us tonight to hear all about what's going on with the sun. We've seen a lot of interesting things in the last little while. Some really strange openings on 6 meters, and for a cycle that's winding down, it's sure making a lot of noise. So, with that, I'm going to throw it over to Scott Macintosh and let you tell us all about it. So,
Oh
Scott,
wow, you're
you're
building
on.
me up too much.
Yeah, well, you got a good haircut, so all right, carry on.
All right, thanks, Paul, and thank you all, and welcome to Wednesday evening. I've got a kind of update on. I was trying to count back, Paul. This is our eighth conversation, I think,
Seems
going
longer.
back, going
Seems more
back
than
to
that.
2021. Yeah, I was trying to see if they went back even further than that, but yeah, there's been a lot of life changes in that time. So I've got less here. I promise you. Um, so let me see if I can bring this up. And before I start, does anyone get any questions, or do you want me to go through this and we can discuss later? Because there might be people that have been on before and um, are either bemused or their closed captioning doesn't work, so they can't understand a word I say or anything. The Google Universal Translator doesn't work so good.
Yeah. Scott, if you this is Roger Oakey. I'm a
Hey,
new
Roger.
newbie here, and
Mhm.
I was wondering if you could, just give a very fast what's your background and where are you zooming in from?
Oh, man alive. All right. I'm from Ukraine. Actually, I'm not. I'm Scottish. It's close enough though. Um, I get confused for an Irishman after 25 years in the US. So I grew up in Glasgow in Scotland. I did my bachelor's and PhD in math, physics, and astrophysics, respectively. I moved here when I just turned 24. I worked at the National Centre for Atmospheric Research for 2 years as a postdoc, and then went to work at Goddard Space Flight Centre for the European Space Agency for 2 years, and then did a further 2 years as a contractor before they tried to make me a civil servant, and I escaped. I came back. Well, the only reason that I didn't hang around at that time, I don't know if it was a good move, bad move, but I would have brought down the median age of the lab by about 25 years. So anyway, um, moved back to work for a place called Southwest Research Institute. It's based in Boulder, Colorado. Awesome place. Left there in 2007 to go back to HAO, the High Altitude Observatory at NCAR. Hung around there, got onto the staff track, and became director of HAO. I was the ninth director of HAO. HAO is the world's oldest solar terrestrial physics lab. So I had the great privilege of being the director there for 5 years before I get sucked into the upper management vortex, um, from which I did not escape until last year.
Last year, yeah.
So, yeah, last fall. So I retired at the age of, on my 50th birthday, with 20 years under my belt and at NCAR, and very happy about that. Anyway, so and ever since then, I've been with a company called Linker. Linker is predominantly a NOAA contractor. They're based in Leesburg, Virginia, but we have an office here in Boulder that does a lot of um, hydrology and space weather work predominantly. And about 4 months ago, we won a contract to support the Space Weather Prediction Center here in Boulder. I've been kind of antagonizing them for a long time. So now I get to work with them. It's all good, right? So because of my background in leadership and subject matter expertise, I get in there to support them on a whole bunch of things. So it's fun. Takes up about a quarter of my week. The rest of the time we're trying to drum up business with private sector companies because the number of objects in low Earth orbit has multiplied from a handful a decade ago to being tens of thousands now. And one of the things that's important there is that the characterization of the atmosphere is not very good. So we have a pretty unique model, Roger, of how the sun works. Very unconventional. Seems to be doing rather well. And one of the downside or upside consequences of that is that it's very good at helping you understand the drag environment, and we can play it out, a very long time in the future. So, we've got a very unique niche in that world. As I was saying before I came on, we're now looking at things like galactic cosmic rays and the South Atlantic anomaly. So protons, charged particles now. Because of the increase in interest in data centers and things like that in space, the ability to accurately forecast radiation dosage on a spacecraft is very important because the computers don't like charged particles, right? So, so all that and all kinds of stuff. I mean, honestly, Peter will get a kick out of this because we're now in the prospect of developing futures trading capabilities, right? Based on the weather.
Oh, on weather base. Okay.
On the weather, right?
Not the proton flux.
Not the proton flux. I don't think there's many futures commodities there yet. But we were joking today that we could have shorted several companies, right? Had we been in business a year ago. So anyway, over a year ago. Anyway, so is that good enough for you?
Oh yeah, and you anticipated one of my questions, which was, it sounded like you were kind of, what you were describing was drag prediction, and you addressed that. So thank you very much.
Yeah, I'm not a drag queen, more of a drag king, I guess.
Okay.
Yeah.
Got it.
So can you make that joke, Paul? Can you bleep that? We don't need to go viral with that one. All right. So anyway, all right. So let me put this in play mode. Can you guys see that? Okay.
Yeah.
Yep. All right. So my pattern with these presentations is always to give them either a crap or a glib title. So this one's a glib one. We're way past max, right? But that's nothing to be worried about for you guys because the way I look at it, we've got at least a year and a half of good propagation left. We can talk about that later on once we turn the recording back off. But probably about a year and a half left. So, and we'll get into how I know that. But anyway, so here's the last time we spoke. It was 6 months ago. Wee bit more than that. 8 months ago. And we were still a little bit up in the air on whether we were past solar maximum or not. Just didn't want to say too much, I guess. The big debates about whether there would be a double peak. Also kind of talk about how the solar cycle's tracking as far as sunspot numbers are concerned, geomagnetic indices. So I think the last time we spoke, we talked about this weird thing called the battle zone, where once we're in the declining phase of the cycle, you should actually see that there's almost like a doubling of the amount of geomagnetic activity because you've got two different sources contributing to the signal. Oh, that's happened. And then, how are the geometric patterns working out? Some of you have been, apologies, at all of these, or many of them. You deserve a medal. And so some of these diagnostics you're used to seeing. If there's stuff, Roger, that I'm going too fast on, just halt me and I can try to explain. So the other point is, where are we in the solar cycle without damaging any of my business opportunities? What comes next? Are there signs of sunspot cycle 26? Maybe someone should ask that question later. And what else have we been doing? So the plot on the left is current, but I blanked out the current area, the current time frame, because this is back to April of last year. And I kind of coarsely call this plot the evolution of man, because it goes from simple to complex, from top to bottom. It's like, simple measure sunspots, butterfly diagrams, more complex butterfly diagrams, and then gee whiz, what the hell is that at the bottom, right? So that bottom thing is our tracker for the full hail cycle. And we've seen that in a couple of presentations in the past. But so if I take away the blocker, you can see that we're very definitely on the downside, right? I don't think there's any doubt of that. But that means that some of the fun is still, we're still in fun mode. I don't think we're going to have a double peak. We can talk about what a double peak actually is. I think that picture is kind of clearing up a lot. But I don't think we're going to have a double peak. We might have some subsequent little fluctuations, but nothing that's going to challenge mid 2024. So this is actually from when I was in my old job, right? So this actually goes back to a presentation from March of 2024 to you guys, right? This is when we were talking about whether we were, were the sun's polar regions reversing. So that meant we were at solar maximum, and all these bizarre geometric things. Well, lo and behold, we'll just zoom in on that a little bit. All of the prophecies have come true, right? So we cruised past the polar reversal process at that time. So you're looking for this time here in 2024. So sometime between January of 2024 and June of 2024 is when the sun's polar regions reversed. And kinda by definition, that means we hit solar max. Right? Solar max and the polar reversal are the polar field reversal are kind of coincident in time. I don't think we ever really can fully understand why that is the case, but it further indicates that there's some weird stuff going on. I'll show that contemporary morphology diagnostic. So this is a tribute to an old colleague of mine, Dick Altrock. He worked down at Kitt Peak, down in Arizona, and he didn't take all these observations because the data goes back to 1939. Some of these were done in occupied France, no comment. Others were done in Hungary, and they were built into a compendium. And what you can see is that your eyes are very good at looking at things. If I go back, you can see the butterfly diagram in these plots. Sorry, I went way too far back. In this third plot here, the third plot down. But that's only part of the story, unfortunately, that there's a much more extended pattern that covers almost 20 years instead of just the 11 of the sunspots. So the sunspots are just a subset of the whole. This is pretty much our ability to diagnose the whole. As of yesterday, this is how that diagnostic looked in the contemporary data sets. This is very pretty. If you look about between 55 and 60 degrees, you can see cycle 26 with the embryonic cycle 26. Because it starts off at about 55 degrees and starts to meander any time in the next 6 months. It's going to take off and start heading towards the equator. Don't ask me how it lingers. Don't ask me what causes it to move. We don't know. All we know that it starts there, or it seems to start there, and that's not even all of us. That's just some of us. That's a tiny subset of my field of maybe me and a couple of other people. Okay. But you can start to see the embryonic pattern of 26, and we'll come back to that in a wee bit. Very interesting because, over the last 4.5, almost 5 years now, we've been talking about how well we can replicate this behavior observationally. You know, the sun is locked in a pattern. It loves to repeat itself. It's not really dynamic. It's not massively changing. And we've seen you guys have basically been tracking this plot since the first meeting. But what you're doing here is basically tracking the evolution of this morphology marker. So by morphology, I mean the sun's global magnetic field is shaped almost like a solenoid, right? It's like a bar magnet almost. And you scan azimuthally around the edge of the sun, and you look at the intensity maxima of the structures there, and you build the image that was on the previous slides. You analyze that, and you start to build up a map of all these different tendrils and loop systems and things, and the lowest order signal that comes out is this one. So on the left-hand side is the spatiotemporal average of that big plot, right? So you basically identify the repeating unit that's in there. And the middle channel is the contemporary data set right now as of yesterday. And then the third panel on the right there is combining the two. So you can see that cycle 25 is basically very average, like very, very average, right? So it's replicating average behavior. Okay. The fun thing is that it's not quite. It's about 6 to 9 months ahead, right? So I can play other games that I'm not going to show that allow me to do pattern recognition on this thing and actually figure out within a month or two's accuracy how far ahead or behind we are. Yes, Peter.
Just wondering, was cycle 25 bigger though than 23 and 24 in
Not
terms of
23,
sunspot
but
numbers?
not 23, but yes, 24 by about 25 to 40%.
Yeah, I figured it'd be bigger. Okay, thanks.
Yeah, no problem. So we'll get into that in a wee bit too. As you remember, this is a infamous plot, or it's an infamous slide, right? Because one of the things that is going to impact you guys is the activity cliff, right? So I call it the activity cliff, but this is basically when the sun stops making a lot of UV, EUV, and X-ray photons, right? So the things that drive the thermosphere and the ionosphere kind of go into hibernation. But as you can see from that plot, we've got a while yet. We're not there yet. Solar Max is there. This plot is 10 months old. So I've got an updated version of it. So you can see how well we done. So white is the model. Gray are 1 sigma variations on the model. Oh, that's right. I was going to introduce the fact that remember that there's 2 things going on now, right? So we've got the light side and the dark side of activity going on. Peter, you might be very lucky and have missed this the first time round. So you've got the bright side of activity, the light side, which would be the active regions and things like that, and the dark side being coronal holes. So the solar wind.
Oh.
So the solar wind starts to come into more prevalence on the downside, right? So what that means basically is that even though the number of it means that the likelihood of geomagnetic activity actually increases because you get 2 different drivers, right? So anyway, why is that? Well, it's because you've got these multiple overlapping magnetic systems. You know, this is the magnetic Hale cycle, all playing out. We'll talk about this a little bit more in a minute. Again, my slides are a wee bit out of sequence. So I'm kind of going back and forth here. All right, so there's the updated plot. How well have we done? The skill score is 0.7 since 2022. So over 4 years, it was locked January 7th of 2022, the forecast. So to recover 70% of the data, I'd say that's pretty good. So I'm pretty happy with that. So of course, the red dots are the monthly values, right? So it's doing pretty well. Looking at the butterfly diagram, how well can we represent the butterfly diagram? Pretty damn well, right? So not only amplitude, but latitude and longitude too. One of the funky things that I think has been really enlightening for us that we've learned a lot about is this idea that the solar cycle can be divided up into 5 kind of equal segments. 0 to 0.2 would be the ascending phase. 0.2 to 0.4 is a bit of a mystery. 0.2 to 0.6 is like this battle zone. So you've now got this battle between 2 magnetic cycles. We hit this cliff, and all of a sudden, all the activities within 15 degrees of the equator, and we can't make spots anymore. And so you start not making a lot of UV photons. So your propagation gets crap. And that stays that way until Arnold comes back to town, right? And somewhere in the middle in there, solar minimum. So it just funnily works out that, there's maybe some beauty in the design here. Anyway, so we'll see a little bit of that in the next couple of slides. So again, back to this idea that the fact that geomagnetic activity is kicking up shouldn't be a big surprise. On the declining phase of cycles, you've got 2 sources of ammunition instead of just the one. Ascending phase, there's only 1 Hale cycle present on the sun. In the descending phase, there's 2. So you've got 2 different sources that drive our atmosphere. And I don't know if it's actually been good or bad for you guys. I think propagation's been pretty good, or has it been weird?
Been weird, but I think the solar wind is the big thing that's making a difference right now on the downside.
What's it doing?
Well, we've seen some good TEP or transequatorial propagation. We're kind of surprised at. We were seeing lack of certain propagation to Japan, which we normally get this time of year.
It was blocked.
It seems to be, it was heading down to, I know it was hitting Hawaii, but it wasn't going to North America. So that was unusual. I haven't heard the JAs for quite a while.
Well, and this is why, right? And that signal's going to become worse. Now, this is the KP index, right? So it's not the day-to-day KP. This is a monthly average KP index. And again, this is a prediction. This is a forecast, right? And the thing that's wild about this, if you look at the sigma error bars, right? So the error bars are very definitely know about some background structure. See how you've got all this variance, but the variance is very strongly tied to where these kind of almost, if you didn't know better, arbitrary fifths of the cycle, right? So the peak at 0.2, which is solar maximum, right? 0.4 is where we're headed right now. 0.6 is a weird one. 0.7, 0.8 is 0.6 is the activity cliff. And then we get solar minimum. But the look at the variance at right now. We're about to hit peak, right? So if I show you where the data goes, so that's a year ago, this is adding the contemporary data. So we've actually done not a bad job. We're certainly within 1 sigma. I don't think anyone's ever attempted this before over this time scale. I don't think the skill score is quite as high as 70%. I think it's probably about 55, but I'll take it. Anyway, as of April 13th last year, this is how things were going when we were comparing observations to contemporary forecasts at the time. So 2022, skill score is pretty good, sitting up there at 0.77. Definitely better than our colleagues that I rib on all the time. And despite a few dropouts, it's actually following the downside actually much more closely than it's following the upside. But the skill score is deteriorating a little bit because some of the dropouts are fairly significant. Some of the peaks are also significant. So like this massive surge in the middle of 2024 was it's actually a 5 sigma event, right? So we had so much activity in May of 2024 that was all predominantly in the northern hemisphere, I think. And it's like a 3 sigma, 4 sigma event over the entire observational history of the sun, right? I'm amazed we didn't end up with more activity than we got, but it was pretty huge. Back to this plot again. So here's our contemporary diagnostics that were updated. I think I updated them yesterday. So this is just another complexity measure. My favorite bright points that I've been cataloging since I was knee-high to a grasshopper at Goddard in 2002. When I first write the code, it's still the original code that runs. So I haven't broken it yet. So this is the data from 2 different spacecraft. Show the same thing. The big thing, of course, here is that pattern of overlap between, I'll draw your attention to 2016 to 2022, when it's clear that there's more than just 2 things. This was the first big insight for us at looking at this, was that how much overlap there was in these systems, right? Because if you just look at the sunspot butterfly diagram, there's no overlap, right, in time. These things are interconnected. And you see that in the very latest data, the 2 activity bands are now starting to impinge upon the equator, which means we get into some times when there could be some very fun sunspots that appear, right? So if you could imagine what a hurricane in the southern and northern oceans would do if they came together. There's this idea in the sun of handedness. So it's called helicity, but left-handed and right-handed magnetic fields. And the ones that destroy themselves the most aggressively are when the 2 meet, when the 2 combine, right? So if you get a southern hemispheric region and a northern hemispheric region that collide with one another, you usually get an absolutely cataclysmic breakdown, right? So we're now entering into the phase of the cycle where something of, without going viral, something of a Carrington type magnitude could happen. Just made a bunch of pretty plots looking at different wavelengths. 2 million degrees at the top. So again, these are just butterfly diagrams covering the span of the mission. 1.5 million degrees, and the brown, that lovely brown shade. Round about 1 million degrees in the teal, and then below 1 million degrees in the yellow. And you notice that the morphology of the atmosphere changes. So if I go back, you see the big coronal holes here. There's not a lot of signal in the teal, but in the yellow channel, you're starting to see the fact that multiple spatial regions contribute to the spectral signal, right? So there's a coronal signal, and then there's a signal from the region that sits immediately below the corona called the transition region. So when the corona goes away, you're left with this much more structured, cooler material that's about 700,000 degrees. I know it's really well to talk about, million-degree plasmas and things like that, but it's pretty cool. Here's the underlying magnetic field. This is a measure that I came up with back 20 years ago to try and characterize the connectivity of the magnetic field, right? So it actually tries to figure out, based on the surface magnetic fields, how big the structures are that are connected to it. So this is a map of distance. So where it's like red, where it's green, it's very small. Where it's red, it's kind of medium. And where it's white, it's very long. Okay. So you can see the polar coronal holes in there. And you can see the activity belts. But one thing to contrast between cycle 24 and 25 is how much broader the magnetic pattern is, right? So if you just do by eye and you do a little Gauss fitting on that thing, 24 was pretty narrow and 25 is systematically wider. right? And like I said, and also 25 is running ahead of time. Another diagnostic that I've looked at that's a derivative of this guy. So again, about 20 years ago, I had a summer student that figured out that we were basically, oh man. So the sun has at least three different scales of convection. One's granulation, so they're a few thousand kilometers across, the size of a continent. Right. And then there's ones that we call supergranulation, which are 20 to 30 megameters across, right? So 20 to 30 million meters across. And then we've got ones that are called giant cells. And giant cells have always just been kind of hypothesized. They've never been uniquely identified. But giant cells are hypothesized to align with the rotational axis of the star, right? And so what we're basically looking at are things that are hundreds of megameters across. So these are massive scale objects, right? But they might form like a hexagon, and all you see are the vertices of the hexagon, right? But they're separated by hundreds of millions of meters. So when we look at this diagnostic, it actually turns out that it's very good at identifying things like coronal holes. Right? You can't see the pattern in here, but if I was to draw circles on this thing, I don't know if the circles popped up because of your lovely faces are covering the right side of my picture here. Hold on, see if I can move them so I can see. Oh yeah, there's red circles there, right? What do you think those concentrate? So if you go back, if I told you that cycle 24 started being visible, or cycle 25 started being visible around 2014. In this diagnostic, you can start to draw your eye back that there's a channel of these pulses of large length scale stuff that starts at about 55 degrees and slowly works its way down to become these dark patches, right? The bright patches that you're seeing at 55 degrees right now are a bunch of recurring coronal holes that are going to become cycle 26. Right? I think I showed an animation of that last time I was here. I should have put that back in these slides.
So
Scott?
are we
Yeah,
going to get
go ahead.
like
I think Paul and I started talking. Paul, you first.
all right, quick question. So these coronal holes are like the source of all these coronal mass ejections. So the larger they are, the more protons.
Coronal holes are the source of the fast solar wind.
Yes. So the bigger they
Okay,
are, the
so
faster they are.
not necessarily. It's not like a volumetric thing. We don't really. Okay, so the textbooks will tell you that it's the expansion factor of the magnetic field that dictates, like a nozzle, that dictates the speed of the wind that comes out. That's not true, right? So there's electromechanical forcing, Paul, that's going on at the bottom of these things. And there's a whole bunch of very high-speed jets that heat the plasma to about 1 million degrees. Once you heat it to 1 million degrees, it can overcome gravity, right? So it becomes like basically more buoyant than its surroundings. And then on top of that, you've got a little afterburner. So each one of those little structures wiggles like seaweed. And that wave runs at about, they run about 1 megameter per second. They're really fast, but they're magnetic waves. And so what they do is they couple into the plasma and they accelerate that plasma up to like 700, 800 kilometers a second, right? So that little jet that goes off gets accelerated out into the solar wind. So the solar wind's full of these tiny little like tadpoles. And it's a micro scale process inside a macro scale object. It's crazy. It's beautiful. And The quiet sun, so where the magnetic field isn't unipolar, is exactly the same process, except there's a lid on the pot, right? So you see all the same things, except for the fact that the plasma can't stream out. It's just trapped in this magnetic bubble. So, yeah, our understanding has increased significantly over the last 10 or 15 years. Yeah, sorry, Roger, you had a question. And
Yeah.
did that answer your question, Paul? Sorry.
Yes,
I think I
yes,
saw a
you
thumbs
did.
up from Paul. Um, Scott, I'm wondering if you could turn on your laser pointer and just occasionally you're using the word you can see there a lot. And being relatively new to this, I'm looking at these plots and I'm not quite sure where there is. So if you
Oh,
turn your
sorry.
laser,
No, my apologies. I can't see the right-hand side of my screen because
okay.
my ugly mug is covering the right-hand side. And I don't know if you can see. Can you see me moving a pointer?
No, but let me see if I can find out where it is.
Oh, I can do it maybe from here.
Yeah.
Yeah, but there's also a laser pointer that you can turn on, and boy, I forgot how to do that.
Oh, let
So
me see
why
if I can do that.
why don't you go on and what I can do is research the laser pointer here, and then tell you when I figured
Is
it.
that
Well,
it?
I might not be able to figure it out.
There's something down the bottom corner of my screen. See, the problem is when I go into present mode, I lose access to my cursor completely. Let's see. There's a little gizmo down here. Oh, that's an annotation tool. So let me keep it at this level just now.
Okay,
Okay.
all right. Thank you.
So these red circles, the ones that I'm circling, they are basically primordial cycle 26. Right? So there's what it's basically showing you is there's a residual pattern in the magnetic field, Roger, of stuff. There's stuff that's forming at 55 degrees for reasons that we don't quite understand. And it's building up in amplitude. Right. And so there's a residual pattern and it's coming through the back. It's like there's like a coherent noise in the background of the magnetic field. Right.
Okay.
And so
Scott,
we can track it through a bunch of different measures. Yes, Peter.
yeah, just at what depth are we looking here on the surface or
This is
above or
basically the surface.
yeah,
Right.
okay.
So
Chromosphere.
these are basically photosphere chromospheric measurements. Okay.
Yeah, okay.
So you start to see that if I flip, it's not so easy to see here. This right here, these dark patches are chronoholes, but it's very hard to see them in a butterfly diagram. If I can go back and when I'm done in a second, I'll go and find the last presentation. I'll show you the animation. So every 28 days, there's a very large chronal hole on the central meridian at 55 degrees. And it's been there for 14 and a half months now, right?
Mm.
Okay. It just sits there and it's changes. It doesn't change in morphology. The most fascinating thing about it is that it doesn't want to go above 55 degrees.
Mm.
It's like there's like a hard boundary there that it's something that topologically it doesn't want to cross, right? But eventually that thing's going to start moving towards the equator about 2 degrees a year, right? We have no idea what causes that. So let's see. So we're looking at this as primordial cycle 26. Let's see if it makes more sense now. You just got to trust your eyes. So believe me, see these dashed lines there? This is a very old plot now. There's dashed lines right where I'm drawing my cursor, Roger.
Yep.
You can
I
see a
can see it.
ghost of
Thank
a
you.
blue thing there and a ghost of a red thing there.
Mm.
Right? So this plot is from like 2012, 2013. And we kind of prognosticated when cycle 26 was going to be visible. So we had a meeting just the other day to talk about writing a paper about this. I mean, it's kind of pointless, but we can do it. So we're going to bring all the diagnostics together to do that. And then, what are we working on right now? Cycle 26 if you read the tea leaves and you've been to enough of these boring presentations, you'll know that the separation between the cycles is the key to the puzzle. And I said that cycle 26 is running, cycle 25 is running about 6 to 9 months ahead of schedule based on our diagnostics, which indicates that cycle 26 may be anywhere up to 25% higher.
Well, didn't you have cycle 26 starting before most others were ready to admit it was 26?
Yeah. 25 for sure. But 26,
I meant,
you know,
yeah, I meant 25. Sorry. And
yeah.
is that delay about the same length as 25 is now?
No. 25 was so behind. So,
Okay.
no,
Okay.
sorry, 24 was running behind, which impacted, you know, there's like it's like waiting for buses in Glasgow, Peter, right? None come and then two come at the same time,
Yeah.
right? And so you get this log jam that builds up. We've got to explore. We still don't quite understand why we think we know why cycle 24 was so weak. And it's largely because of things that happened 22 years ago, right? So the Halloween storms, one theory is that the Halloween storms destroyed so much magnetic flux, right? Because if you remember 2002, fall of 2003, we had some major geomagnetic activity for months. And the theory is that, or our theory is that you destroyed so much magnetic field that you actually slowed the dynamo down, right? And now it's just starting to recover. I've not been paying attention to any of the questions in the chat yet. So, um, so 26 is looking good. There will be a cycle 26. You're welcome. You know, it might be about as good as I can say. We're studying things like the SAA right now because it's good for people that are building data centers and trying to put them in space, right? Other than the thermal problems that they're going to have trying to dissipate all the heat, which I don't know how they'll solve.
What's an
But
SA?
the South Atlantic anomaly, right? So you know what that is? Have you ever seen it? Right. So this is an animation. So you see the time ticking away here. So it's a blob of increased radiation. It's basically what happens because I think the Van Allen radiation belts, because of asymmetry in the Earth's magnetic field and the tilt angle, the Van Allen radiation belts actually tilt into the atmosphere, right? So you can actually measure the radiation flux. And it creates a highly distorted field. It's not Bermuda, don't worry. It creates a highly distorted electromagnetic field, right?
Mm.
So if you're flying from Brazil to Europe, for example, the SA is one of the things you worry about for HF comms, right? So it's a aviation risk, but it's to do with the fact that there's probably also some weirdness in the mantle magnetic field there. I'm not a geologist, but what I will tell you is that in analyzing the 45 years of data from orbit, the SAA has been migrating westward at about 0.3 degrees per year, right? So that means that whatever's going on in the magnetic morphology underneath has also been migrating westward at 0.3 degrees per year.
Is there any correlation between that and the pole, the North Pole's migration?
So probably yes. I'll get into a question for Peter in a second, right? So this is a purely Peter question that's coming up, right? So, but I'm not going to blow up the plot because it would destroy my business. But that plot that's second from the right shows the evolution of this stuff over 40 years. And so you can see a very strong decadal scale signal in the data. So the SA pulsates with the sunspot cycle. It shifts in latitude and longitude with the sunspot cycle. It varies in tilt angle with the sunspot cycle, but not quite. So that's where I'm going to leave that. I'll leave that for another day. My one question for Peter is, right, this is a highly controversial one, Peter, right? So we've been looking a lot at the potential effects of particles on weather, right? Weather, not like
Yeah.
weather on Mars. And my buddy has a bet on with me that if I integrate for long enough, so I can take all these measurements, so these are polar orbiting satellites. If I take enough of the data, he's put a bet on with me that the Aleutian Low will be antipodal with the SAA. So the Aleutian Low is maybe a geomagnetic phenomena.
Yes.
So I don't know if any of you know about the Aleutian Low, or maybe everybody knows about the Aleutian Low. But, so he's was very curious. So we've got 40 years of data that add up. Because if it's there, it might be a very weak signal. But there's some odd stuff. And I know that the Canucks do a lot of studies up in that area because it affects a lot of weather patterns on the west coast of Canada. In the Bering Sea, I guess.
Bering Sea. Yeah.
So anyway, we've been looking at stuff like that. We figured out a way to model and recover the galactic cosmic ray flux, so we can actually forecast the GCR flux out with the sunspot cycle. So we're doing all kinds of things now. We're trying to, because it turns out that like I think I said at the start, when you're building hardware to put in space, charged particles are not your best friends, right? Drag is one problem, but charged particles are also not your best friends. And if you're on, for example, the satellite that the astronauts in the ISS worry about the SAA, right? So they fly through that thing occasionally. And so if it's particularly intense, during a proton storm, they have to go into their specially shielded capsule. So anyway, that's about all I've got. I hope some of that made sense. I try not to bore you. I try to bring something new to the table every time, because otherwise it'd be really dull.
Hi, Scott. Handle here is Adrian. Got
Hey,
a
Adrian.
couple of questions.
Yeah, go ahead.
First of all, do you know what caused the Maunder minimum? And secondly,
Oh,
do you think you could,
okay.
do you think you can predict one?
Oh, wow. Have you got $10 million?
Ha
Because that's what the answer costs. No, I'm kidding.
Yeah.
No, I think I do, but I thought I did. And we're starting to learn some odd stuff that I think I can observationally challenge my own idea. Right. So, but basically we wrote a paper, Adrian, back in 2014. You can go find it. That talks about the formation of grand minima. And basically I haven't really talked about this in any detail. I've not really focused on much other than contemporary stuff here. But, I'm fairly certain that the Dalton minimum, which is far better observed than the Maunder minimum. Well, that's not true. The Maunder minimum was very well observed. But the Dalton minimum, 4 or 5 cataclysmic geomagnetic storms took place the decade before Dalton. And this goes back to Peter and the ice core stuff that I was talking about earlier. We think that the same thing that happened with the Halloween storms that quenched cycle 24 really quenched cycle number 4. Right? So cycle number 4 is a total wiener. And that's the start of the Dalton minimum. Right? So one hypothesis is that in the lead up to the Maunder minimum, we had geomagnetic activity that was off the charts. Now, the problem is it's hard to test, right? So the only people that were cataloging geomagnetic activity at the time were Captain Cook and his buddies.
Yeah.
And so getting to the Admiralty records is one of my passion projects, right? So they're starting to digitize the Admiralty records in London. And I would love to do an AI study to go through and look for reports of St. Elmo's fire and things at low latitude. So you're looking for low latitude storms, right? So anyone crossing the equator and try to build a catalog. So that's one way of doing it. So you can have so much geomagnetic activity that you basically stall the dynamo. I'm not sure how you do that in a passive way, right? But the fun thing is though, one of the questions is that we know about the Maunder minimum. We know for sure from the isotope records is that even though the sun was not making many spots, the solar wind was still cycling on an 11-year basis. Right? So we were still making coronal holes. So the stuff that's going on at high latitudes was still going on at high latitudes. Right? So the sun's poles were opening and closing, the solar wind was appearing and going away on the same timescale that it was before the Maunder minimum and what it was after. So the only thing that happened was happening in the mid latitudes. So it's a complex puzzle. Sorry, go on.
Just basically shut down the sunspots, and that's kind of it.
And our hypothesis is that if you have too much overlapping systems, I didn't show it in here. I can dig it out in a minute. But if you have our whole system, our whole hypothesis based on the overlapping and interaction of magnetic cycles, right? So magnetic systems always want to be net zero. That's probably a bad phrase to use these days. But, magnetic fields always want to cancel. And so you can get into a situation where for a long period of time, you just, in sunspots, you need imbalance to make sunspots, right? So if you get into a system for a long period of time where your big magnetic systems are all balanced off by one another, you can't make spots. There's no asymmetry in the system. So you need to break the symmetry. And the thing that seems to break the symmetry is the fact that there's this high latitude clock, right? So that the high latitudes every 11 and a half years, boom, drive. And eventually that kicks you out of this kind of stagnation. So there's like two different theories there. I don't know. One of them is very testable by going and looking at records for low latitude events. Interestingly enough, the Dalton minimum is you can diagnose it from ice core samples. And this is my follow-on with Peter, is that there was a series of events in 1790 to 1794 that precedes the Dalton minimum. And then these big geomagnetic storms actually persisted for the next 20 years. And then this all of a sudden they went away. And the sunspots came back, right? Like this sunspot the cycle amplitude came back to normal within 2 or 3 cycles. So there's a long residual memory in the system, right? So anyway, I did not illustrate or answer your question well, but I kind of tried.
Oh, it's a glimpse.
I've got a question, Scott.
Yeah. And then Peter. Go ahead, Chris.
Your opinion of Frank Stefani's comment in spaceweather.com recently that the tidal forces of the planets are affecting or have always affected the 11-year solar cycle.
Wow. Did I comment on that?
No, that was Frank Stefani said that on spaceweather.com.
I know Frank.
It was printed up. It came up
it
about
doesn't
a week
work.
ago. About a week ago on spaceweather.com. And it did mention that it was highly contentious.
Doesn't work.
No.
It doesn't work for a simple reason: energy density. right? So gravitational energy density is nothing compared to the Coriolis force, right? So everything I've been talking about is driven by the rotation of the star, which is driven by its own gravity, right? The gravitational force of Saturn and Jupiter compared to that is zero. It's like 9 orders of magnitude less.
Oh, okay.
So the other problem you have is it's a magnetic phenomena. It's not just about tidally making things erupt on the sun, right? So you would see. I think that there's enough mess in the signal of the sunspot cycle where you can convince yourself you see all kinds of periodicities, right? What we've tried to do is stay away from that and only study the magnetic effects, right? So we're basically saying if you can't explain where the Hale cycle comes from, you're not even in the right game, right? So by them messing around with tidal forcing to make sunspots, you're not even there. I don't know how you can understand magnetic variability by looking at tidal forcing because magnetism and gravity are so different, right? It would be such a small
too small of a
perturbation.
player, right? Yeah.
Way too small of a perturbation, but they don't go away, right? And it's okay. That's part of science. But I would love to see them try to predict what we've done, right? If you really think you can do it, look at the conjunctions over the next 5 years and get it a skill score of greater than 80%. That's a challenge. I bet they can't do it.
Mm-hmm.
Oh, this is going out on the internet, isn't it? Okay.
Proof is in the pudding, though, you're saying.
I bet they can't do it.
Oh, the glove has been thrown.
Yeah, we'll challenge them at cycle 26. We'll do it now. How about that?
Well, this is interesting. The 6 to 9 month ahead of time for cycle 26 has given me incentive to stay in shape so that I'll still be alive for that. Scott, thank you very much.
Yeah, no, it'll be worth it. Hopefully it'll be worth it. I mean, you're not quite at cycle 19, but you're getting closer. So anyway, yeah, it's a very interesting theory, and it's really interesting, Chris, because what the average sunspot cycle duration is 11.86 years. What is the orbital period of Jupiter? 11.8 something years, right? So that's the crux of the argument.
Yeah, that they mentioned that in the article. Yeah,
And that's the crux of the argument. It's that I don't think the energy density really matches up.
Yeah.
So, I mean, it could have been very important back at the start, right? You never know. So I think these things are all very, the phrase self-organized criticality, where everything's kind of very much on a manifold and it just takes a little tilt to the manifold to set it wobbling. I think that there could be an influence from that stuff, but it's third, fourth, fifth order magnitude. So anyway, I'm more worried about Rossby waves and rotation, to be honest. So, hey, Peter, go ahead.
Yeah, I was wondering, Scott, given several comments you made in that you affected the slowing down, or the effects you were describing were affecting the slowing down of the dynamo. I would have thought that would be possibly the other way. That's the dynamo that would be causing the effects that you see. Can you differentiate between the sort of the energy levels here? I mean, the dynamo strikes me as being a massive device inside of a very massive object, and
are you
therefore
trying to
has
say I'm
some kind of a
contradicting
time
myself?
constant to it.
Are you trying to say I'm contradicting myself?
No, I'm asking a deeper question, I guess, and because I want to ask, in fact, how your work might even affect any observations we've made with other G stars.
No, it's a brilliant question, right? So there's a few diagnostics, and maybe the next time I come on, we'll dig into the ice core stuff, right?
Okay, that'd be great.
It's fascinating, right? Because if you told me that the tail can wag the dog, I'd say you're fucking nuts, right? However, we're looking at a large interconnected magnetic system that always wants to be in balance. So if you can disturb the balance, right, or think about it, if you can destroy half a cycle's field in a couple of months, right? So it's all about this large coupled device, right? So one thing you've got to think about is, and this is highly, highly controversial, right? Our model leads us to believe that the magnetic fields are absolutely dominant in this puzzle, right? Our colleagues, not to mention the folks that worry about, orbital alignments, believe that the magnetic fields are completely passive to the global scale circulatory flows, right? So the global scale flows do everything. Now, one event that we didn't talk about in this conversation, but we've talked about a lot in the past, is the Terminator, where the Hale cycle ends at the equator, and then all of a sudden, as if by magic, activity springs to life at mid-latitudes, like within 28 days. That is not a diffusive process, right? So, stars shouldn't do that shit, in other words, unless they're magnetically connected, right? So, our hypothesis works off the fact that this is just a large magnetofluid, right? Where instead of the M in magnetohydrodynamic being a mu, it's a capital M, right? And at times and places it dominates the flow. And so if you can destroy enough of that field, it can slow down the system, right? That's a simple hypothesis, right? That if you can destroy enough of the field in a short amount of time through cancellation, right? So you make big storms. You actually, so now if you think about it, if the amount of flux creates an electromotive force for these bands to pull, the bands are basically pulling themselves towards the equator. They're not stuck in any flow. They're just trying to cancel, right? And the fluid's just in the way.
Could a Clarington event be triggered in that sort of activity you're describing?
Yeah, it would be a cataclysmic thing like that.
Yeah. So have you looked at any correlations between recorded events on Earth, both in terms of, the more recent time Carrington event, but also the various minimum that we've had in the past in terms of climate, the Sporer minimum, the Bonder minimum, etc., and then the warming periods, like the Roman warming period. I mean, the Roman Empire grew under a rather benign climate.
Right. I mean, we haven't really dug into that stuff very much, Peter, because there's just not... The observations become very challenging, right? So so you can go back to the 1600s pretty well, but the problem there is the telescope. The telescope was invented in 1602, right, or there or thereabouts. Before that was the naked eye observations, which were very sporadic. It's really challenging, right? And so and even if you think you can convince yourself, there's a lot of contrarian stuff about the ice core samples now, right? So there's like, oh, it was a biomass burning event. It wasn't really nitrates. It's like, well, is it nitrates or not, right? Where did the nitrates come from? And so there's like people trying to, I don't know if it's people from Climate World or what, try to pour hot water on that problem. It's fascinating. I mean, I really, really, really want to get into those Amrapli records and see if I can, look around that 1600 or 1625 timeframe and see, are there an increase in geomagnetic storms? It's the kind of thing that people would report in passing. There was a red glow on the horizon, right? But the dudes on the boats were very meticulous about the weather.
And they said almost fire.
Yeah, it's the only place where I think you get a decent enough reporting record, right? Maybe in the Spanish Navy and the Portuguese Navy too. So, I mean, I think that stuff's absolutely fascinating. The mechanism, I don't know.
Yeah, the British Navy did have a rule about taking, bucket temperatures at a regular interval on lats and logs as they sailed across oceans. I don't know
Well, and
whether
you,
other, yeah, I don't know
well, they
whether
did.
other nation states did that, but the British definitely had a Navy had a bucket temperature program for their ships at sea.
Yeah, and the guys were very meticulous about reporting, the general weather conditions and blah blah. The question, the thing is always deciphering the observer, right? Every observer is going to have a slightly different process. So, but it's amazing stuff. Would love to dig into it. I think that's probably one of the clues to help you disambiguate what if the 5 or 6 possible things could do it. Because if it's our hail cycle stuff, then you have to explain that it can slow down to a point where it basically stagnates. And it's just in constant lockdown. But then, the fun bit is that even though it can be in permanent solar minimum conditions, which would explain why you would have the poles doing their thing at the same time, you can still have Rossby modes longitudinally, which means you could get, even though the sun's making no spots, you could have times when the buoyancy locally becomes large enough to make spots in one hemisphere for a couple of rotations and then they go away again, right? Because the imbalance is now driven by the buoyancy wave as a function of longitude. So it's a real mind fuck, really, and it's not a
But
very well constrained mind fuck.
But is this assuming that the changes all around are there's a fixed dynamo, but the dynamo is not changing?
Yeah, I don't know if it doesn't change though. I think
Yeah,
well, I mean, obviously evolutionary on the stellar timescale it changes,
yeah, a stellar timescale for sure.
but I think you can have cataclysmic events that slow it down for a little bit, and it's a paper that it's a method, it's a theory that we've published, right? We know how to diagnose it. We've seen. I think I showed that before. So, like when you look at Hilbert transforms
Yes, you did show us
of
those.
of the sunspot data, you can actually see this time where there's a phase shift, and those almost always coincide with major geomagnetic events. So why would the sunspot number reflect a major geomagnetic storm, right? Other than the fact that it's doing some damage to the internal mechanics somewhere, right? So anyway, it's a bloody amazing problem. It doesn't keep me up as much at night as it used to, but I would love to take a sabbatical and spend 6 months. Maybe I can make my $10 million and go and spend some time in a musty old basement in London.
Yes, well, Admiralty Arch is where the books must be.
Yeah,
The records.
but I from what I gather, they're starting to digitize them all.
That would help a lot.
So
That'd be
anyway,
good.
Hey, you've done some really great work here for us today, and this is awesome. Unfortunately, a lot of it's over my head, but I'm sure some of the other folks are understanding it a lot better than I do. But
I think you sent them all to sleep, Paul.
I don't think so. But thanks again for everything you've done here, and we'll do a summary of this if I can get AI to help me out here, and
Right.
see if we can put that out to the folks, and have another great have a great session here with you. But thanks
Yeah,
again
I'll see you.
for
I'll see you
everything.
in another 8 months, right?
Well, hopefully not that
Or
long.
less, or less.
Yeah.
Or less. When we wait till we can definitively see cycle 26 and we can go, look, see it, there it is.
Yeah.
It's exactly where we said it would be.
So, Scott,
But
I did have a question, and I don't want to hold us up here, but I was just wondering: has your work been applied, or do we even have the data, as in sensitivity, to see other G stars in any kind of cyclical behavior?
great question, right? So, I'll give you a quick answer. We are starting to. There's a survey that's done out of Lowell Observatory in Arizona, And they've been cataloging, so they use a spectral polarimeter, Peter. So
Yeah.
that's one essential component, right? The calcium variability indices are great, but they don't help you diagnose anything. They just tell you that a star is kind of quasi-periodic with this time scale. What we really want are the magnetic cycles.
Yeah.
And the problem with that is you can only look at G-type stars that are pull on to you,
Yeah.
right? So you'll still catch the calcium index variability stuff, but what you want to do is see the poles evolving through the Doppler magnetograph, right? And we're starting to look at some of that stuff. It's a very not the most dense data set in the universe, because what we basically be looking for is signatures of other stars like the sun doing exactly the same thing, right?
Yeah.
So we'd be looking for polar evolution on a similar timescale. And then you would try to say, okay, well, if that's got the same kind of Hale cycle pattern, can we use our knowledge of the sun to back out what that star's doing? Right. So it's kind of like the solar stellar connection working in the solar stellar way instead of the stellar solar way, which everybody also always assumes that the sun's the weird one. Right. In that world, they assume that the sun is the weird one, not the other stars. But I think they've been looking kind of at the wrong. I don't
Well,
think that the calcium index.
I would suggest many variable stars are probably the really weird ones,
Oh well, they're really truly weird. Like Paul, yeah,
especially the
yeah,
solo variable stars. I
Cephids,
mean, not ones that are being circled by other stars.
yeah, the Cephids and things like those are mental
Yes.
stars. Yeah,
Yes.
but rather benign things like our peaceful star,
It'd
right?
be curious.
So
It'd be curious to see what metallicity has an effect on.
yeah, I think I would. What I'd really love to see is a range, right? It's because our gut instinct tells us that geometry is the key factor here. And geometry is set up by gravity, set up by mass, right? So it all kind of comes down to mass and age, right? And because 55 degrees, for whatever reason, is extremely important, but that might not be the same for all stars, right? So if you get brown dwarfs with deeper convection zones, it'll look a bit different, right? So they might look a lot more like Jupiter, for example, where instead of having 2 bands per hemisphere, you have 20. Right. So here's another diagnostic. I'll throw this out on the YouTube. Right. One of the things we were thinking about doing is taking the Earth's most sensitive spectral polarimeter, which is on a telescope in Hawaii. So there's a 4.5-meter solar telescope in Hawaii, and try to get permission to point it at Jupiter. Why would you do that? Well, Jupiter's atmosphere is not highly ionized. But if you were to look for magnetic fields at the interfaces of those bands, maybe there's enough ionization to, the reason that Jupiter has so many bands, of course, is because the core is rotating at some wicked rate, and it's only 1/10 of the depth of the atmosphere, right? So what we'd actually be looking for are spectral polarimetric signals at the interfaces of the rolls, right? Because these are convecting rolls. So we'd be looking for very weak magnetic fields at the interfaces. And that would be a scaled up version of what the sun's doing, because the sun only has 2, right? But Jupiter has 20 per hemisphere because of the rotation rate. So sun-like stars would be easier than that, but it's not easy to get funding for that. So I think if we can generate enough internal R&D money, where we can take our eye off what we're doing for a little bit, we can go and start to dive into this database at Lowell. It's really beautiful. The instruments are one of a kind, because astronomers don't like magnetic fields, generally speaking, and so they don't put polarimetric experiments on these big telescopes, right?
Well, there are
because
those interested in magnetostars.
yeah, but those rotate like fuck.
They certainly do, but there may be a relationship here.
Oh,
I mean,
I'm sure that
after all,
it's
they're
like
stars.
stars gone wild, right? It's like the 90s. So
Well,
no,
the rock
absolutely.
stars, yes.
I think the thing that gets you there is just the speed of the variation. So I would honestly love to look at stars like the Earth that are Polon that have other exoplanet systems around them, right? And start to ask that habitability question. So anyway, no, it's really fascinating stuff.
Yes, the Green Bank equation.
Well, thanks for the questions there, Peter. And thanks, Scott, for everything you're doing here. It sounds pretty exciting. We're doing some pretty exciting stuff down at Haswell, which we'll talk about later.
Is it going well?
Yeah, really well. We're getting our deep space network set up this weekend to do some real deep stuff. See if we can pick up our friend Voyager 1, and I see Voyager 2's now in the gone past the edge of our solar system. So we can see if we can pick up those guys with our little dish.
Well, that's cool. I haven't seen the press releases of late.
The
other thing they did recently, Scott, is tried to do a bounce off Venus.
Well, we're going to do that again, maybe this
When the
fall.
time's right. Yeah, next year or later this year.
Sweet.
October.
Sweet. So you're telling me that I miss out on too much when I don't show up. Is that what you're telling me?
You got to come on down to Haswell sometime, and I'll give you a hamburger. So.
You've advertised these infamous hamburgers.
Very infamous, that's for sure.
Very infamous.
Thanks again.
All right, I'll take you up in that. We'll go down in the summer.
All right. Sounds like a good idea. Take care, guys. And thanks for everybody joining us tonight. And we'll be putting this video out on YouTube later this week. And I should have a summary of what we discussed tonight.
Take care, guys. And Peter, I'll reach out to you about ice cores and stuff, okay?
So thanks, Scott. And thanks a lot, Paul.
Thank you, Scott.
See you guys.
Paul.
Cheers, guys. Bye.
73.
Thank you, Scott.
73 is all.
Thanks, Scott. Hey, Paul.
See you, Dana. Take care.
You look
Bye.
Bye.